Hi, my name is Ryan Zbikowski. Thanks for stopping by my presentation. The title of my talk is Bootstrapped, Block Lanczos for the Large Dimension Eigenvalue Problem. Let's dive on in. All right, to understand my research, you got to understand what Lanczos does. The Lanczos algorithm takes a given matrix H and then iteratively constructs a new orthonormal basis called a Krylov subspace. So each iteration of the Lanczos algorithm makes something called a Lanczos vector. You can use those Lanczos vectors to make the matrix you see to the right, matrix H. Now, the top left-hand corner of that matrix H converges rapidly to the eigenvalues of your original input matrix. So you don't have to diagonalize the entire space of your input matrix. You can just get some of the low-lying eigenvalues very quickly. This is great because the matrix is very large. You can't use things like householders, so Lanczos is a good choice. Now let's talk about block Lanczos. Block Lanczos is just like regular Lanczos, except you replace the matrix vector multiplication with matrix multiplication. So instead of a tridiagonal matrix H, like you saw last slide, to the right you see H, which is block tridiagonal. This leads to faster time to solution because you improve the data locality. Typically, when you run either method, Lanczos or block Lanczos, you have to pick have some kind of starting vector, like a random vector, or in the case of block Lanczos, a random block. Well, come to find out, maybe the random block isn't the best choice. So we recommend bootstrapping your initial pivot block. That is, replace those random vectors with vectors which are approximations of the part of the eigenstates you're actually interested in. Okay, so how does this relate to nuclear structure? Well, in the research that we do, we're interested in solving the non-relativistic many-body Schrodinger equation, which can be cast as a matrix eigenvalue problem. And that matrix is, and the matrices we work with are very sparse. How sparse, you ask? Well, 1 in a million matrix elements may actually be non-zero, so very sparse. And what we're really interested in is getting a few of the low-lying eigenstates. So you can see to the right, you see a plot of the nuclear excitation spectra of beryllium-8. That excitation spectra corresponds to the eigenstates of the nuclear Hamiltonians that we're trying to get the eigenstates of. So block Lanczos is fantastic for this. And what we do basically is we compute the approximations of the low-lying spectra in some truncated model space. We project them into the full model space. We cram them into the pivot block of block Lanczos, and we run it. And then we see if it actually improves the performance of block Lanczos. And it does. Let me show you that. Next slide. All right, our results. The plots A and C are for beryllium-7, our first test case, dimension 6 million. And you can see in the blue, and then plots B and D, second case, dimension 141 million. Same configuration between for both. Plot A shows that, yeah, block Lanczos takes more iterations than single vector Lanczos, but if you bootstrap the pivot with an approximation, you find that it actually runs in many fewer iterations. But to understand what I mean by truncation and sort of that number in the legend, that little blue box, that number actually is the fraction of the truncated model space to the true model space. So we're actually using tiny model spaces that are very easy to compute. And when you project them, they still produce massive gains in timing and massive reduction in the number of total Lanczos iterations. So look at plot C, we can see that because of the improved locality, that sure enough, regular block Lanczos, the conventional block Lanczos random pivots, runs about twice as fast as standard single vector Lanczos. But if you bootstrap the pivots, you find out that you run about twice as fast as conventional block Lanczos. Fantastic. Now, if you go to the larger model space, again, you see a lot of Lanczos iterations for conventional block Lanczos. Single vector Lanczos runs fewer iterations. But if you bootstrap the pivots again, we see massive reduction, total number of iterations. If you go to plot D, you can actually see again, this is actually interesting because we're actually pushing the boundaries of our machine. This is a very large problem. And since n corresponds the number of vectors in your pivot block, for very large dimensions, you can actually have situations where block Lanczos underperforms single vector Lanczos, and that's what you're seeing for block sizes greater than 4. But if you bootstrap the pivot, once again, we see dramatic improvement in performance, and you can get incredible improvements in timing. Block Lanczos runs about twice as fast as single vector Lanczos. Bootstrap Block Lanczos runs about twice as fast as that. So, wow. All right. Thanks for stopping by. Have a good one.